Welcome to this machine learning case study. Today, we're going to be covering the paper titled Machine Learning Driven Optimization of Arsenic Phytoextraction Using Amendments. So arsenic is a toxic soil contaminant that can be remediated through phytoremediation using hyperaccumulator plants such as Pteris vittata. Arsenic removal by P. vittata varies from 0.02% to 13.2% depending on field conditions. P. vittata phytoremediation can be improved by increasing soil arsenic bioavailability by mediating chemical reactions that facilitate redistribution of arsenic from the solid to liquid phase, and the promotion of P. vittata biomass production and arsenic accumulation ability by providing nutrients or enhancing antioxidant capacity. Amendments to enhance phytoremediation efficiency are not widely used due to efficiency uncertainty and limited information on its economic sustainability. So for this study, the authors trained a random forest model to identify and optimize the key parameters that impact P. vittata arsenic accumulation using amendments. The authors also investigated the cost effectiveness of various amendments. Data was collected from the literature related to enhancing phytoremediation of arsenic by P. vittata. 2,299 data points from 121 data sets with 19 variables grouped into 4 categories were collected. These categories were P. vittata, amendments, soil properties, and cultivation condition data. Random forest regression predictive models were constructed to identify the primary factors affecting how amendments enhance arsenic extraction efficiency in P. vittata. The random forest permute package was then used to calculate the significance levels of the importance of each feature variable. 80% of the data was used for model training and 20% was used for model evaluation. Highly important features were fitted using the ggplot package to evaluate their impact on P. vittata arsenic accumulation. Indicators used to evaluate model accuracy were the coefficient of determination, or R-squared value, the root mean square error, or RMSE, and the mean absolute error, or MAE. The R-squared value needs to be as close to 1 as possible to indicate an accurate model, and the RMSE and MAE values should be as low as possible. Features most important to enhancement of phytoextraction efficiency by amendments were assessed by mean decrease accuracy. And this is the increase in the mean squared error after randomly assigning values to each feature variable, with a larger value indicating that the corresponding variable is more important. For the economic sustainability step, this integrated market prices, application rates, and phytoextraction efficiency to assess the economic sustainability of each amendment using this equation here. The ERC, or enhanced remediation cost, represents the cost of amendments required to assist P. vittata in removing an additional 1 gram of arsenic from the soil, with lower values indicating better economic efficiency. This p-value indicates the unit price of the amendment. A is the application amount or dosage of the amendment. E is the enhanced arsenic phytoextraction amount due to amendment application. And the K is a unit conversion constant. So this is the overall study workflow. Again, data was collected from literature related to the P. vittata, soil arsenic, and enhanced phytoremediation subjects. And these were the amendments that were selected to be studied. 121 data sets were collected with features of amendments, soil properties, and cultivation conditions. All of these were used to predict the target of P. vittata behavior. These were plugged into a random forest model with these evaluation metrics. Then the important features and parameter optimizations were identified. Then that data was used to estimate costs by taking into account things such as unit price, dosage, and extraction volume, and the economic sustainability of different amendment types was determined. So for results based on arsenic accumulation, changes in plant arsenic accumulation ranged from a 62.6% reduction to a 4,767% increase, depending on amendment type. Effective amendments listed from highest to lowest were phytohormones, phosphorus-based fertilizers, non-phosphorus fertilizers, microbial amendments, organic amendments, and chelators. So this figure here shows that the R-squared values were pretty close to 1, and the RMSE and MAE values were fairly low. The most important factors in the arsenic accumulation change were biomass production, types of amendments, and arsenic concentration within the soil. Changes in P. vittata biomass production ranged from a 77.1% decrease to a 1,514% increase. A strong positive correlation with change in arsenic accumulation was found. Amendments that promoted growth were phosphorus and non-phosphorus-based fertilizers, organic amendments, and phytohormones, while chelator amendments actually inhibited plant growth. So for the biomass change results, the R-squared value was pretty close to 1 for the training set, but less so for the test. And it was a little bit higher for the test set regarding the RMSE and MAE values. Factors that were the most important for biomass change were the types of amendments used, the duration of cultivation, and the application time regarding the amendments. And for the arsenic concentration change results, again, the R-squared value was close to 1 for the training set, but not for the test set. And the RMSE and MAE values were low for both the training and test. The most impactful factors for the arsenic concentration change were types of amendments, available arsenic in the soil, and application time. So now taking a look at the economic sustainability results, the enhanced remediation costs of each amendment ranged from 0.57 to 3,903.86 Chinese yuan per gram of arsenic. Phosphorus fertilizers displayed the lowest ERC value at a range of 0.57 to 121.64 Chinese yuan per gram of arsenic because they are traditionally used in agriculture and are produced at a very large scale, which keeps market price down. Amendments listed from most to least cost-effective are the phosphorus fertilizer, natural organic acids, microbials, synthetic chelators, and organic amendments. Phytohormones and surfactants were not included in this comparison due to the lack of data. So to conclude, the increase in biomass production has a larger impact on arsenic concentration elevation on P. vittata phytoremediation efficiency. Optimal plant growth and biomass maximization must be prioritized over amending the soil to increase arsenic bioavailability. Phosphorus-based fertilizer amendments are the most cost-effective solution to enhancing phytoremediation of arsenic-contaminated farmland. So if you're curious to learn more about this study, you can find it at this full citation. Thank you for watching.